All right, so we're here to talk about the relationship between a probability distribution and a sample that's based on that probability distribution. So as I said before, we're thinking about a sample as being the result of repeated probabilistic events. So each time you do an event, you're adding to your sample. So here, as an example, I'm going to say, let's say that we want a sample of 10 outcomes for a double coin flip. And we want to know, out of those 10 double coin flips, what's the what number would we expect to be, 0 heads, 1 heads, or 2 heads? And what our probability distribution tells us, so I'll just say here, our probability distribution tells us that we should expect a distribution that looks like this. So we should expect about 25% of our outcomes to be zeros, about 50% of our outcomes to be ones, and about 25% of our outcomes to be twos. Now we're talking about 10 coin flips. So thinking back to relative frequencies, to get to a proportion of 0.5 out of 10, that's going to be 5 out of 10 coin flips. So 5 out of 10 coin flips would give you that 50% value we're talking about. But in order to get a 25% proportion out of 10 coin flips, we're talking about either 2 or 3 out of 10 for both of these. So what we expect here, the frequencies that we expect to get either 2 or 3 zeros out of these 10 events, because that'll give us either 20% or 30% zeros, which is as close as we can get to 0.25 when we're talking about 10 coin flips. We would expect to get 5 ones as outcomes. So we'd expect 50% of our 10 outcomes to be ones, that means 5. And we'd expect 2 or 3 of our outcomes to be 2 as the value, because 2 out of 10 would be 20%, 3 out of 10 would be 30%, so it's the closest we can get to 25% if we're talking about a sample of 10. And so what I'm going to do here is I'm actually just going to flip this coin 20 times, so that'll give me 10 events of 2 coin flips, and actually count up the outcomes and see what we get. So that's our first coin flip. Our second coin flip, so that was a tails and then a heads. That means we have 1 heads out of that event. All right, so we got a tails, followed by a heads. That's another one here. We got a heads, followed by a tails. That's another one here. So again, we're sort of populating this sample. We're adding outcomes to our frequency distribution just by flipping this coin a bunch of times. There we got a heads and then a heads, so we got 2 heads as our outcome. We're up to 4 events here, as you can see. Got a tails, and then another tails. So that was 0 heads as the outcome of that trial or that event. Heads, heads again. So that was 2 heads as the outcome of that event, and so on. Throwing my coin all over the place. So that was a tails, and then a heads. So we got 1 here, heads, tails. 1 here, so let's see, we have 5, 6, 7, 8 events so far. We're going to go all the way to 10 here. There's a heads. Oh, goodness. And then another heads. Which gives us 2 heads. And then for our final flip here, we've got a tails, and then a heads, which gives us 1 heads as our outcome. So here, what I'm demonstrating is that we can think of this as being like a sample of 10 events. So of all the possible outcomes we could have, we have 10 of them written down now that we tried by flipping this coin. And what we can see is that our frequency distribution here, and I'm going to rewrite this, I think. So our actual frequencies that we got 0 heads 1 time, we got 1 head 6 times, and we got 2 heads 3 times. So our actual frequencies are kind of similar to what you'd expect for based on the probabilities, but they're not exact, right? So we said that we expected 25% of our outcomes to be zeros. Here, we're dividing each of these into 10 to get our relative frequencies. Here we had 0.1, or 10% of our outcomes come out to be 0 heads. We had 0.6, or 60% of our outcomes come out to be 1 heads. And we had 0.3, or 30% of our outcomes come out to be 2 heads. So what we have here is a frequency distribution based on 10 events. And it does somewhat resemble our probability distribution, with our expected probabilities, but it's not exact. And this is generally how sampling based on a probability distribution works. We have more ones than anything else. Our relative frequency here, so the percentage of ones out of our 10 outcomes, is close to 0.5, right? It's 0.6, but it's not exact. Our percentage of twos is 30%. Sorry, this should say proportion, and then I could also write percent. So our percentage of twos in the sample is 30% for a proportion of 0.3, and that's close to what we would expect based on our probability distribution, where this is 0.25. But again, it's not exact. And as I mentioned before, sample size is important here. And as a general rule, the bigger your sample is, the closer these values are going to be to what you expect. So I'm not going to do this, but let's imagine that I flip this coin 2,000 times. So that would be 1,000 separate events here. The more times you flip the coin, the more likely it is that you're going to fill in the events as expected here. So if you did this 1,000 times, you would generally expect to have about 25% of those 1,000 events to have an outcome of 0, 50% of those 1,000 events to have an outcome of 1, and 25% of those events to have an outcome of 2. And you'd expect those proportions to be pretty close to these numbers here. Because with that many different coin flips, it's unlikely that you're just going to happen to get, say, 2 heads, more times than you'd expect. Unlikely things tend to even out when you have a large number of events like that. Now imagine that you flip it 1,000,000 times. So the more times you flip the coin, the more likely it is that your distribution is going to look like the probability distribution. And this is an idea that we're going to come back to later, so I'm not going to keep going on and on and on about it now. But the takeaway here is that the bigger your sample is, meaning the more events you do, the more likely it is that unlikely outcomes are going to sort of even out over these many, many different events. And your frequency distribution is going to end up looking more like your probability distribution.